My name is Wilbur Ouma. So technically my position at the Ohio Supercomputer Center is called client engineer, but I don't have an engineering background. So I would like to call myself a research computing facilitator. And that's my main role at OSC, at the Ohio Supercomputer Center, to make it easier for researchers, students to use the facility for their research, for their data analysis, and for their simulations. And I also am involved in creating training programs for the same. So like introduction to supercomputing at OSC, and also some topical training workshops like data analysis with applications like R, and also some bioinformatics pipelines like analysis of RNA-seq data. So that's my main role. I'm also involved in technical support, like help users that are using the system to solve issues that they might be having, like troubleshooting their code, and just help them to start using OSC like during onboarding processes. My background is in biology. I obtained my bachelor's degree in biochemistry from the University of Nairobi and my master's in bioinformatics from the University of Nairobi in Kenya. And then I came over here for my PhD at the Ohio State University in a program called Molecular Cellular Developmental Biology, but my focus was on the computational biology of transcription factor binding and gene regulation. Yeah, let's get started with this introduction to supercomputing at OSC, OSC being the Ohio Supercomputer Center. And I understand that some of you already do have experience with HPC systems. So that is great. And for those ones that do have much experience with HPC system, just bear with us. Some of the concepts I'll be talking about might be repetitive for some of you, or might be too basic for some of you, but I'm just trying to do this to make sure that everybody is on the same page when it comes to using the Ohio Supercomputer Center. And so yeah, that's the introduction to the supercomputing at OSC. I've already introduced myself, but what I want us to talk about today is, first of all, to just give a brief introduction of what is OSC. And then I'll talk about some HPC concepts. And by this concept, I'll just be defining things like nodes and clusters and cores and GPUs, generally just the hardware of the supercomputer. And then I'll talk about an overview of the actual supercomputer that we have at OSC, the overview, the hardware overview of the cluster, like how many nodes, how many types of processors we have. And then briefly, I'll talk about the user environment. So, and then later I will talk about using software that we have installed on the OSC systems. And then lastly, hopefully we will have time, I will demonstrate a dashboard that is called On Demand. And this dashboard will enable you to log into the clusters and start using the clusters for your analysis and for your simulations. Okay, so what is the Ohio Supercomputer Center? OSC is a state agency in the state of Ohio, and it was founded in 1987 through the Department of Higher Education. It's a statewide resource for primarily universities in Ohio, and we do provide high-performance computing services in terms of HPC clusters and storage. And also we do provide services in terms of computational science expertise. In as much as it's primarily for researchers in Ohio, we do collaborate with researchers outside of Ohio. And we do provide these services to all those researchers across the nation and also across the world. Our service catalog in brief comprises of these 5 components. And the main component is cluster computing. And in cluster computing, we have these machines that users can log into and perform analysis and perform their simulations, right? And I will talk about what these machines look like in a moment. Another service that we provide is research data storage. And this is large capacity data storage that makes it easier to access the data during data analysis, but also for long-term data storage and archival. Education is also a very important component for us, and we try to create both live and also asynchronous training events to make it easier for OSC users to use the cluster. We do also have a web software development, and the experts that we have in web software development try to create custom web interfaces that simplify the use of the powerful HPC resources. One of the web interface that I'll be talking about today, it's called ondemand.osc.edu that was developed at OSC. And then lastly, we have the scientific software development component, and we have scientific applications team that develops software that takes advantage of the large compute clusters that we have. So I'll switch gears a little bit now and talk about different HPC concepts, just defining some of the terms that I'll be using in today's presentation and in the demonstration part of it. So one of the things you might be asking yourselves, why use HPC for analysis? And I actually see like there are three main reasons why you might consider using HPC for your analysis. Top on the list is speed. So your simulations or analysis that you're performing might be taking too long on your personal computer. What HPC systems offer is more and faster cores or CPU that you can use. You can take advantage of multi-threading, and you can take advantage of also multi-node parallelization. In this case, you're using all the CPUs across multiple nodes. And you have a framework for that called MPI. You can also take advantage of some hardware that accelerate analysis and simulations. And these are the graphical processing units, so the GPUs. We do have NVIDIA's CUDA GPUs installed. And you can also take advantage of distributed computing to speed up your analysis. The second reason you might consider using HPC is just probably because your data is too large to be contained either on the hard disk or to be accessed in memory. In that case, you can take advantage of the large memory nodes that we have. And by memory, I'm talking about the random access memory that you have. And by storage, I'll be referring to the actual physical hard drive that you have on the machines. So we have nodes and compute nodes that range from 700 GBs to as much as 3 terabytes of random access memory, and we can take advantage of that. And lastly, you might want to use HPC systems simply because they do have software stack that is important for your analysis, and maybe you don't need to go into the trouble of installing all the software. For instance, at OSC, we have about, I think, close to 150 software installed already. So you might first of all just check on the list of the software that we have. And then if that software is available, you just go ahead and load that software environment and continue with the analysis instead of going through the trouble of compiling or installing some of the software. So how does the cluster or the supercomputer differ from your desktop machine? You can just think of the supercomputer as, thousands of your desktop machines on steroid, because you just, amplifying the power that you have in one of these computers. So you have your computer, and then you can easily connect remotely to the clusters. And right now, I just want to give a bit of a distinction between the HPC systems and other systems that are out there for analysis, like the Amazon instances or the Microsoft Azure instance or cloud services. So HPC is a little bit different from cloud services in the sense that for HPC, you are actually connecting to the physical machines, and you're using physical machines for your analysis. You're not necessarily spawning virtual machines. While in Amazon, for instance, when you start an Amazon instance, you're actually starting an Amazon virtual machine or an Amazon container that has all your software installed in that particular container version. And once you're done with the analysis, your virtual machine is gone, your your container is no longer available, but you can access that container by just starting it. For an HPC system, you're actually logging onto a physical machine, and you can request access to a certain number of computers or a certain number of nodes and a certain number of CPUs and or GPUs or even storage to access. So you're actually working with a live physical machine when you're dealing with the HPC system. So I've been talking about nodes, computers, clusters, GPUs. Let me just give a brief description or definition of this particular HPC terminology that I've been using. When I talk about a compute node, what I'm talking about is a compute node is just equivalent to a high-end workstation that is part of a cluster. Think of a standalone computer, and this standalone computer has its own associated CPUs or other accelerators like GPUs. It has its own associated random access memory and also storage associated with it. So that will be one compute node. Now, when it comes to a compute cluster, like the Ohio Supercomputer Center clusters, we do connect thousands of these compute nodes together using very fast internet connectivity called InfiniBand. And that makes it easier to request multiple compute nodes to speed up your analysis or to speed up your simulation. So within each of this particular compute node, we have CPUs, and sometimes I'm interchangeably using the term CPUs or cores, and this is just a central processing unit. And these CPUs have their own associated memory. So for example, for most of the nodes that we have at OSC, CPU will have about 4.5 GBs of memory. And then that means that if you request a compute node with 10 CPUs, that means that you are actually having access to 10 multiplied by 4.5 GBs of memory. We also do have this multi-core processors that are called GPUs, and these ones are really optimized to handle very many small calculations. These are very attractive for machine learning and deep learning applications in terms of accelerating those processes. Yeah, so in summary, when I talk about a cluster at OSC, I'll be talking about an interconnected network of multiple of these thousands of these compute nodes, right? And each of these compute node is actually, you can think of it like a standalone computer, that it has multiple cores associated with it, and also storage associated with each of these particular compute node. And if we zoom out a little bit, we can actually now take a larger view of the, or appreciate a larger view of the structure of the supercomputer. I've already talked about these compute nodes, which are in thousands. We have thousands of these compute nodes. They're all connected, so you can actually request access to more than one of these compute nodes. And apart from that, we have other components of this particular supercomputer center. One of the most important components is the login components. So you will be able to log on to this particular compute nodes using one of these two main methods. The first one is using the terminal, and in the terminal, you just open up a terminal window on your local machine, and you can use an SSH protocol to just SSH to the machine, to the login node at OSC. And of course, you first of all have to have an OSC account to do that. And I hope we've been given all that information. Create an OSC account, and then we will put your OSC account, your OSC username, onto a project account. And once that is done, you should be able to open a terminal window, SSH onto the login node. So we have two main clusters that I'll talk about. So you have to SSH to a specific cluster. One is called Owens and another one is called Pizza. And I'll give you instructions on how to SSH. So that's one way of connecting to the clusters. The other way, which is actually, we found that this is actually the easiest way, and most users are using this way, is to use a web portal that I'll be demonstrating at the end of this presentation. And this web portal can be accessed by going to opening your browser of choice and going to ondemand.osc.edu. You'll be prompted to put in your OSC username and password, and then you'll connect to the login nodes. So for each of the two clusters that we actually have three clusters, but two clusters are available for general use. So for each of those two clusters, you will have access to one of these login nodes. And we do have thousands of users trying to access these clusters, this compute node specifically. So once you're on the login node, you will be able to request access to our compute node, because you will not be able to perform, high-level computations or simulations on your login nodes. You will need to request access to a compute node, and we have a system in place and a software that receives all those requests and then allocates resources based on resource availability. But while still on the login node, you'll be able to access data storage. Each user at OSC will have 500 GBs worth of storage space. So this is for each user, and nobody can get access to that home storage. Sometimes the PI of a project can request additional shared project storage. And when you have shared project storage, that means that all users on that particular project at OSC can have access to that particular project storage. And this one is typically in the range of terabytes, 1, 2, 20, 50, 100 terabytes of shared storage. Each user also has access to Scratch storage, and Scratch storage is just temporary storage. For instance, if you're performing an analysis that is generating hundreds or even thousands of temporary files, you might want to consider performing that analysis in Scratch and then just save your results either in home or project storage. And the reason is because Scratch storage is temporary storage. It's not backed up, so it's usually purged after 90 days. So you might want to consider putting your data either in home storage or in project storage. So generally, that's how the structure looks like for the three clusters that we have. You have the login component. Through the login nodes, you'll be able to access your compute storage, and you'll also be able to request one or more of these particular compute nodes for analysis. And if we talk about specifically the two clusters or the three clusters that we have at OSC, this is how they look like. So I'm going to use just first of all an infographic to give you a general overview. First of all, I'm going to talk about Owen's compute cluster, and then lastly, I will talk about Pizza compute cluster. They are quite similar. The structure, the architecture is the same. The difference is that when you log on to Owens, you will only have access to Owens environment, meaning Owens software that have been installed on Owens and the hardware on Owens. So you'll not be able to move from Owens to Pizza while you've already logged on to Owens. If you submit a request on Owens, your job would run on Owens, but you can still log on to Pizza and you'll have an environment specifically for Pizza, all the software installed on Pizza, and you can perform also your analysis on Pizza. My understanding is that right now our scientific applications team is installing almost all your software on Owens. So there's a likelihood that you'll be using Owens most of the time for your analysis, because that's where you'll have your software environment. You can still log on to Pizza, and unfortunately for Pizza, you will not have all the software that you need for this particular, for the upcoming workshop. So just keep that in mind, that we have software being installed on Owens. Log on to Owens, you'll also use one of these two methods, either a terminal, shell window, or the web portal. Then you'll get access to the login nodes. We have different types of compute nodes on Owens. The commonly used type of nodes are called standard nodes. We have 600 of these, and each of these standard compute node comes with 28 CPUs per node. So you'll have 28 cores per nodes that you can request on each of the nodes on Owens. In addition to that, if you request a whole node on Owens, you'll have access to 128 GBs of random access memory. So that is the commonly used standard compute nodes. We do have other nodes on Owens for specific pipelines. And one of the nodes that we use that we have on Owens are what we call the data analytics nodes. These ones are slightly larger than the compute nodes, the dense compute nodes. While these dense compute nodes have only 28 cores per nodes and about 128 GPUs of memory per node, the large memory nodes or the data analytics nodes on Owens have significantly more memory. We have 16 of these, and each of these have 48 cores per node, and they will have about 1.5 GBs of memory and about 12 terabytes of local disk space. So we have significantly more cores that we have on this particular data analytics nodes on Owens. But for the most part, you will be using the standard nodes for your analysis. So most of you will be requesting these particular standard nodes. Sorry, this is not 1.5 GB. You have 1,500 GBs of memory, so 1.5 terabytes of memory when you request a whole compute node or a whole data analytics node on Owens. We also do have specialized nodes for GPU acceleration. Owens has 160 of these GPU nodes. And these GPU nodes are just like standard nodes whereby they have 28 CPUs per node, but in addition, they have one GPU for GPU acceleration, GPU hardware. So that's the total number of nodes that we have on the Owens cluster. We also do have another type of nodes that we call debug nodes. These are just for debugging purposes. If you have a code and you want to debug it for about an hour before you submit a job to the cluster to run, you can use this particular debug nodes on Owens. Pizza system, the architecture is quite similar to the Owens system. You also have the login component. You have a choice of the terminal or the web portal ondemand.osc.edu. You will get access to the login nodes plus the shared data storage components. Pizza is a little bit heterogeneous in the sense that, first of all, the first time it was commissioned, this was in 2018, but then recently this was expanded to include an additional number of nodes. So before expansion, we used to have about 200 standard nodes on Pizza. Now, Pizza is slightly larger than Owens, whereas the standard nodes on Owens were about only 28 CPUs per node. Each of the standard nodes on Pizza that most of you might be using will have 40 cores per node. We also do have special kinds of nodes for GPU acceleration, like GPU nodes, and we also have huge memory nodes. So I don't think most of you will be using this, but supposing you're running an alignment, let's say, or you're building you're performing what is it called? A genome assembly, and it's taking too much time and it's not able to fit in the memory that you have on a standard compute node, then you might need to consider a large memory or even a huge memory node that have 3 terabytes of memory instead of 192 GBs of memory for a standard compute node. So we have this as the original nodes that we had on Pizza. And as I mentioned, Pizza was expanded in 2020 to include additional number of nodes, additional standard nodes, additional large memory nodes, and additional GPU nodes for analysis. So most of these other nodes are for specialized pipelines, but you can still request access to them. For example, if you have a pipeline that is using GPUs for acceleration, you can request access to GPU nodes on Pizza to speed up your environment. So that is the hardware that we have. Mostly Pizza and Owens. We have another cluster that is called Ascend. It's mostly GPU heavy. It's not available for general use. We just do provide access to Ascend cluster upon request for specific pipelines. So I'll switch gears a little bit now and move from the hardware and talk about software and the user environment that we do have at OSC. Our clusters run on Linux operating systems, specifically Red Hat. And this is Unix-like. It's used in most HPC systems. It's mostly command line, and you do have a choice of the shell that you want to use. You can log on to the system using SSH terminal window. You'll have a Linux shell, and then you can perform your analysis. But we've tried to simplify use of these HPC clusters by using the on-demand portal that I will demonstrate later on. So if you don't have a lot of experience in Linux, let's say creating files with some editors and moving through navigating yourself across different directories and paths, you might still get away with it if you use the on-demand web portal. But for most computations in bioinformatics and computational biology, basic understanding of Linux system is really, really important, and it will help you to go quite far. It will make your life easier, actually. So how would you start connecting to the cluster? Of course, as I mentioned, the first thing you have to do is to make sure that you have an OSC account, a username that you'll create. And then that username will be associated with a project account, and then you'll be able to connect to the cluster. I did mention that you can connect either using the SSH terminal window from your local machine, or you can use the on-demand web portal that I'll be demonstrating. Just remember that if you're SSHing, if you're using SSH from your local machine terminal window, and if you're going to render any applications that have a graphical user-based interface, you have to use an X11 forwarding in order to render those applications on your local machine. If you're using on-demand portal, you can just start what we call a desktop session, and I will demonstrate how to do that. And with that desktop session on demand, you can start applications that have a graphical user interface. We already have also some applications installed that have a GUI interface on ondemand.osc.edu, and I'll show them in a moment. So two main ways of connecting to the cluster, using the terminal window SSH or using the web portal ondemand.osc.edu. There's several ways of transferring files to and from the cluster. You can use protocols such as SFTP or SCP, secure copy, to transfer files from your local machine to the cluster and the other way around. ondemand.osc.edu also offers a file explorer option that enables you to easily drag and drop files from your local machine to the cluster. But on-demand works well for files that are less than 5 GBs in size. If you have larger files, then you might consider using rsync or Globus system for file transfer. And of course, if you have files that are stored in let's say an SFTP server somewhere else, let's say NCBI, and you want to download them using either wget or curl, you can easily do that also through the terminal window once you log on to the cluster. Okay, so once you log into the cluster, you'll have access to software environment that we've already installed. You still also can install your own software in your home directory or even in project storage. You have that ability to install your own software that we haven't installed. And especially if it's an open source software, you can do that. You can run your own binaries on the cluster. So you don't have to just use the software that we've installed or that we are maintaining at OSC. We have about 150 of those 150 software packages that we've installed and we are maintaining at OSC, so that we try to keep them up to date, and we have different versions that you can select from. There is a web page, and you can check if your software of choice is already installed at OSC. The most important thing to remember is that we have two main clusters and they're actually separate. So you might have a different version of that software on Owens and another version of that software on Pizza. So just keep track of that. We do have several general programming software already installed. For example, compilers have been installed. We have an MPI library that is really important for parallel processes requesting multiple nodes. We have Python installed. Most of you might be using this for your analysis. And also we have R, statistical and programming environment installed. You can access R either through the terminal, or you can also start an R Studio server session through the on-demand web portal. And I will demonstrate how to do that in a moment. We do also have software applications for parallel computing. If you're interested in parallel computing, we have MPI libraries, and we also have open MP libraries for multi-threading. If you're going to use GPUs for acceleration, you'll need CUDA libraries for that. We do have those ones installed. You just need to load the environment, and then you'll have access to those particular parallel programming software. So most software licenses that we have are for academic use only. And if they're proprietary software, then we have a license for that already. And to access some of those proprietary software, you'll have to reach out to us. You send an email to OSC Help, and then we can add you to the license server. For example, if you want to use, I think Stata is proprietary, MATLAB is proprietary. So those kind of software, you need to first of all reach out to us so that we can add your OSC username to the license server to enable you to use. But a majority of the software that we have are actually open source. You can just log onto the system, load the software environment, and then start using the software. If you do have a software that you want to install, you can go ahead, especially if it's open source, you can go ahead and install it, right? If it's a commercial software and you already have a license, you can install it, and then we can work on how we can get access to the license server, either where you're hosting it in your institution, or we can have it hosted at OSC. As I mentioned, software, we are loading software environments at OSC. So when you log onto the cluster, in order to use a specific software, you have to load that software in your current session. And there's several couple of commands that you can use for managing software environment. For example, if you want to look or to take a look at what are some of the software that have already been loaded in your current environment, you can just type module list on the terminal. You can take a look at what modules are available for that particular software by using module spider or module avail. And I will demonstrate all these commands in a moment. You can load a specific software. Let's say you want to perform an analysis, genome alignment using BWA. You'll have to load that BWA software using module load BWA. In this case, you're loading a software called CUDA, or you can just load module load CUDA. And you can also swap between different software versions. It's really easy to load software environment at OSC. It's really easy to install your own software, and especially if it's open source software. It's really straightforward. You just use the same process like you do when you're installing software on your local machine. Just remember that you will be working on a Linux system. Now, I'll talk about batch processing, and then after batch processing, I'll give a demonstration of on-demand, and then I'll take questions. So batch processing is a very important component, concept for you to understand. And the reason is because supercomputers have to use queuing. And the supercomputers, the nodes that we have and the CPU that we have, those are limited resources. And we typically have 2,000 to 3,000 people logging onto the cluster on a particular day. So what we do have in place is a system that manages all those requests to use the compute node. Typically, what a user would do is that they will write what we call a batch script. And in this batch script, they will just tell the scheduler at OSC, what resources they are requesting. For example, how many nodes they are requesting, how many CPUs they are requesting per node, and for how long they think their analysis will run on that compute node. So typically, each of the users will log on to the login nodes, and then they will write a small script, and I'll show you an example of that small batch script, and then they will put all that information, and then they will submit that to the scheduler. And then we'll have a queue of all these, what we call job submissions from hundreds or thousands of users. And then what the scheduler will do is that it will look at each of these submissions and then look at available resources. So let's say, for example, you want to perform an alignment that will only take 2 hours, and someone else is performing a simulation that will take 7 days. So the scheduler will look at the queue, look at these two requests, and then most likely will allocate compute resources, compute node on the request that is actually requesting only for a couple of hours. And then these other requests that is coming in that wants to use the supercomputer for 7 days might have to wait on the queue for a while for resources to be available. So just keep that in mind. You might submit a job if you're requesting access to a compute node for, let's say, 2-3 days. You might have to wait on a queue for maybe a couple of minutes, 20 minutes, or even an hour before your job actually runs. So that's what's happening with the batch system. And to request, and so the process in summary of running a job on this particular compute node will involve creating a batch script for that particular job. For some of the analysis, you actually will not have to create a batch script. For example, if you're going to run an RStudio server application, instead of creating a batch script using a text editor, you will just go to on-demand, and then you go to interactive applications. You're going to fill out a form, right? It's a web form, and I will show you how to do that. On this web form, you will specify how many CPUs you want, how many nodes you want, for how long you want your analysis to run. And then you'll submit that form, and then it will be on the queue. That form is actually just a batch job that you're submitting for the scheduler to look at and then to allocate resources based on the availability. For some of the applications that you'll be running, let's say genome alignment using BWA or using Bowtile or using cufflinks, if it's a command line based application, then you'll have to write a job script in a text editor. You'll have to specify resources, and then you're going to submit that particular script, the job script or the batch script. The job will get queued, and then once resources are available, your job will run, and then you'll get results. And in that kind of submission, you don't have to sit there and wait. As long as you have your batch script specifying the resources and then including the commands that you're trying to run, you submit it to the system, and then you'll come back later and then look at your results once your job completes. So a typical batch script will contain information such as the number of nodes that you're requesting and the number of cores that you're requesting per node. And also if you're requesting accelerators like GPUs, you'll include those ones also in the batch script. And then optionally, you can also specify memory, but the amount of memory that you're requesting is actually, it corresponds to the number of CPU that you're requesting. So this is optional. And then the wall time is very important. Wall time is you're estimating how long your analysis is going to run. And for most people, it's fine to overestimate a little bit. So if you're performing a genome alignment or an alignment of transcripts, right, of RNA-seq data, and you feel like maybe my alignment will take, let's say, 5 hours, it's okay to overestimate and put 8 hours or even 10 hours. And if your analysis only takes 2 hours, that is fine, it will complete, and then your job will end, and then you'll be able to relinquish those resources. The challenge of wall time requesting is that if you do not request enough wall time, let's say your analysis was supposed to take 5 hours and you requested only 4 hours and 40 minutes, right? And your analysis is not complete, unfortunately, that job will be killed because of you did not request enough wall time. So just keep in mind when you're doing that, and you might end up losing your results because the job might be killed. So it's always good to overestimate a little bit. The downside of overestimating is that if the system is quite busy, you might have to wait on the queue for a couple of minutes, 15, 10 minutes, sometimes, 20 minutes sometimes. But it's much better to wait for a couple of more minutes and for your job to run to completion than for your job to start immediately, only to terminate simply because you did not request enough wall time. The other thing that you'll include in your batch script is your project number. That is very, very important. And I think instructors will give you the project number at OSC that you'll be using for your analysis. And then if you're using any software applications that have licenses, then you'll have to you put a flag for software licenses. But I think for most of you, you're going to be using open source applications, so you don't need to worry about software licenses. So this is a sample SLAM batch script. SLAM is actually the scheduler and the resource manager application that we use at OSC. So you'll have all this information in a text editor, in a text file, right? The first thing that you'll put is the job setup information, meaning you're requesting a certain amount of resources. The first line in this text file is called a shebang line. You're just specifying the shell that you want to use. There's a question, is it possible to use Schrodinger suite packages to run MDS, it's commercial packages? Yes, it's possible. So for those ones, I think you'll have to send us an email on OSC help, and then we will add the username to the license server in order to run Schrodinger. Okay, so you'll put all this information, or you're requesting resources. You'll put the shebang line. If you forget to put the shebang line, it's fine. We have a compatibility layer in place that is able to include this. But this way, you're just specifying which bash, which shell to use. In this case, you're going to use bash. And then you're going to specify resources using this sbatch directive. You're going to put this # sbatch space, and then you're going to specify the time. Excuse me. You're going to specify the wall time. In this case, you're estimating that your analysis will take about 1 hour to run. So you have hours, minutes, and seconds. And then secondly, you'll specify the number of nodes that you want to use and the number of CPUs per node that you want to use. In this particular example, we are requesting for 2 compute nodes, and we have n tasks per node, specifying the number of tasks. By default, the SLAM system that we have at OSC, the number of tasks corresponds to the number of CPUs. So in this case, you're requesting for 40 CPUs in each of these 2 nodes. So you'll have access to a total of 80 CPUs. Just remember that if you're requesting more than 1 node, that means that your application is able to take advantage of parallel processes. So that's an MPI process. Okay. Question, what Linux distro is needed? Linux, Mint, or Ubuntu, or any other? So for you, you don't need to install any Linux distribution. We already have Red Hat at OSC, so we run on Red Hat. So you don't need to install on your end anything. Okay, yeah, so you'll specify the number of nodes. For most of your analysis, you'll actually just be putting here 1 because you'll be using 1 node and a certain number of CPUs on that node. Now, in this example, we are specifying 40 nodes. And in the system specification that I talked about a while ago, we say that a normal or a standard compute node on Owens has 28 CPUs per node, right? So Owens doesn't have, unless you're asking for large memory nodes, but for standard compute on Owens, we'll have a maximum of 28 CPUs per node. If you're running a script on Pizza and you want a complete node, then you can put either 40 or 48 CPUs per node. So if you have a script like this and you're trying to run it on Owens, you might end up getting an error message. And the reason is because we do not have standard compute nodes on Owens that have 40 cores per node. So you might have to change this number to 28 in order to get a complete or a whole compute node on Owens. But this one can run pretty well on Pizza system. But the point is here, remember, if you're using more than 1 compute nodes, then it means that your application is an MPI application. Otherwise, you'll have to use 1 node and a certain number of n tasks per node. And then you can put your job name. And then most importantly here, you have to specify your account. And I think your instructors will tell you which project account to use. So all the OSC users will have a project account. You'll have your user account, which is your username, and your username will be associated with the project account. You will not put anywhere on this batch script your username, right? You'll only use your username to log into the system. Then once you're in the system, you'll create a text file, and then you'll specify the account, the project account to put here. So this is the job setup information for SLAM, and the SLAM system will look at this information and then provide resources based on resource availability. Then once you're done with that, you can now start to put commands to be run. And as you notice, these applications, this batch script mostly will run commands or applications that have a command line interface. Okay, there's a quick question here. If you want to connect to OSC using shell, then on your laptop, you'll have to make sure you can have SSH. Yep, that's correct. Yep, thanks, Amitava. Yeah, so after the job setup information, you will put your commands of interest. You can put this, sorry, excuse me. You can change directory, and then you put SLAM submit directory. This is just a variable, environment variable that directs you to the location where you have this particular SLAM batch script. And then the next thing we'll do is you will set up your software environment. In this example, we want to compile. We have to load Intel, and then you can copy your data into the temp directory. This is actually optional. And then you can run your commands of interest, right? You're compiling this particular code in C to get this output binary, and then you're running that output, and then you're copying your results from the, the temp directory to your SLAM submit directory. So you'll put this information in a text file, your job setup information, and then the commands that you want to run. And then you're going to submit it into the SLAM scheduler using a command called sbatch. And this is just a summary of the commands that you're going to be using. So you'll have sbatch, and then you specify that job script, right? So this would be your job script in a text file. You give it a name, and then you submit it to the scheduler using this command, sbatch, that will submit the job script. Once the job script is submitted, you'll get a message like this, a response like this, submitted job, this submitted batch job, and then you have a job ID. You can go ahead if you want to cancel. If you realize that maybe there was an error and you want to cancel that submission, you can just put cancel, then you use the job ID. And then you can also look at the status of whether that job is already running or it's still on the queue by using this command sq-u, and then you put your OSC username. I'll try to demonstrate how to submit batch jobs once we are done with the on-demand demonstration. So, excuse me. So, I've talked about submitting a batch script, and once you submit that batch script using sbatch, you can log out of the system and come back later. You can actually also include directives here to get an email when your job starts to run, and we have all that information on our website at osc.edu. So once you've submitted that one, you can log out of the system and then come back and look at your results. Another way of running batch jobs is just to run them interactively, right? So you're still requesting access to a compute node, but maybe you just want to be there on the terminal and run your applications. Maybe your applications are generating a graphical user interface, or you want to run your commands line by line instead of waiting for your results from the batch system. So you can actually do that. You can just start an interactive session, and hopefully we'll have time. I will demonstrate to you, or I will show you how to start an interactive session. It's the same thing. For example, you just put this command sinteractive, and then you specify the project with -a. You specify the number of nodes that you're requesting with the uppercase N. In this case, I'm requesting for one node. And then the lowercase will just be requesting the number of tasks per node or the CPU that you want to run. And then -t, how long you want that analysis to run. So when I put this command on the shell terminal on the login node, I will be given access to the shell on a compute node. And then I can just go ahead and start, running my applications on a command line basis. Again, if you're using parallel computing, you can take advantage of multi-threading, whereby you're using multiple CPUs on one node. You can also take up advantage of message passing interface, whereby you're requesting for multiple nodes to accelerate your analysis. In one of the batch script examples that I'm going to use, we're going to use multi-threading option. Just remember that to take advantage of parallel computing, especially if you want to use multiple nodes, the software application that you're using should be able to do this, should be written in a way that it can take advantage of parallel computing. So simply requesting more number of nodes does not necessarily mean that your software application is going to run in parallel. So you have to make sure that the application that you're running actually takes advantage of multiple nodes in order to run efficiently in parallel mode. Any questions now before I start demonstrating? I think that's enough for the presentation. So I'll take any questions before I start demonstrating ondemand.osc.edu, because I think that's a very important one. And I will share the slides after this so that participants can review them.
So I have an accounting question.
Okay.
Philip, Phil already put the PSG account number that we should use. And our workshop starts on 14th, 15th, depending on when you are. Can I ask the users to follow the steps that Wilbur is showing to be familiar with the batch system, but not use any heavy calculation, any demanding calculation until the workshop start? Okay, so just get familiarized with S-batch, S-interactive, and all those, but please do not start any demanding calculation until the workshop start. And there is another question for you, Wilbur, or for me. Oh, I do not.
Muted.
Maybe you can answer it. You can answer it better.
Yeah, for SSH, you actually don't need to install. My understanding is that I don't have a Windows machine, but my understanding is that the latest Windows machine comes with a terminal window. I might be wrong, but I know. Yeah. So if you have my understanding is they have a terminal window. You just open the window and they have an SSH functionality. All the Windows machine, I think you had to use something called PuTTY or PuTTY, something like that.
Wilbur, if I can just intervene.
Yeah.
So on other Windows machines, ideally I would recommend installing something known as WinSAP, WINSAP, and also PuTTY. And if you link the two, yeah. So if you link the two, then it behaves just like a typical Linux terminal.
Oh, cool. Yep.
Yeah.
For the on-demand, yeah. Thank you so much. Yeah. If you have a Mac, then you don't have an issue with that. Or if you have an Ubuntu installed, then you don't have an issue with that. You just open the terminal and then you SSH. For example, you'll SSH, if you are connecting to OWNs, you'll put something like SSH, and then you'll put let me put that in chat. SSH, you'll put your username. My username is that one, and then at owens.osc.edu. Right. And if you're connecting to Pizza, of course, you'll Ouma, that is my OSC username. So you'll replace that with your OSC username. If you're connecting to Pizza, it's the same thing. SSH your OSC username at pizza.osc.edu. But also there's a comment here. Yep. Thanks, Vish. But it's actually also easy just to connect, if you have a Windows machine, to use the on-demand dashboard. And I hope everyone can see my browser.
Yes, so we can see it.
Okay, good. So if you already have your OSC account, the username, you can go to ondemand.osc.edu. Let me just put that in chat. ondemand.osc.edu, you log in. I'm already logged in, so I can log out. So you'll go to ondemand.osc.edu, you log in with your OSC username and the password, right? And once you are in, you can access the shell by just coming to clusters. And I think for most of you, you'll only see 2 clusters. So you can select which cluster you want to use, either Owens or Pizza. If you want to connect to Owens, you just click on that, and then you'll get your Owens shell, but on the login node, right? So if you're running any applications that are command line based and that you don't need to render any GUI interface on your local machine, this is also an easier way. So if you have a Windows machine and you know that all the applications that you'll be running will just be command line for the most part, you can use on-demand shell access, right? And here you're on the login node. And then we can now start creating a batch script here to submit to the SLAM scheduler, right? But if you're going to render graphical interface, then you might need to use a terminal window with an X11 forwarding one, or you can come and start what we call a desktop interface. If you start a desktop interface, you can start running applications that have a graphical interface, right? In the desktop interface, you just fill out this information. It's like you're starting a batch session. That's why you have to specify the project, you're specifying the wall time, how many cores you want to use, how many nodes you want to use, if there's any software license for the applications you want to run. Typically for the node type, for a simple analysis, I just leave it any. It will give me 28 cores on Owens. Those are just a standard compute node, unless I want to use GPUs, for example, or huge memory applications. And then I will click launch. And this one is going to be queued because I'm submitting it to the batch system, right? But I'm going through this Owens desktop simply because maybe I wanted to SSH minus X11 on the terminal on my local machine, and I'm having issues with that. Okay. So once this one is ready, you just click your Owens desktop. Okay. And then you can have access to your applications. You can also start a terminal window here, an emulator. And if you have an application that, let's say you have binaries that when you open or when you run, they create a GUI interface. If you run them here, right, you'll get that GUI interface. And then you can just submit your jobs, okay? You can actually perform your analysis using the graphical interface. But this is a workaround for, applications that have a graphical user interface. I'm working from home and there is a delivery that just came in and it's really, really important. So I'm going to be right back in 5 minutes.
I'll take over. Yeah, I'll take over from here. Yeah, thanks.
Okay, I'll be right back. Sorry about that.
No, that's okay, Wilbur. Thanks. It's an interesting presentation. Okay, so some of you you do not have an account on OSC. Now, you should, if you accepted the offer to participate in the workshop, you should get an email from OSC, especially from Phil Thomas, who is with us. He's arranging for all of you to get account on OSC. I can see at least 2 of you did not have an OSC account. If you put your email address in the chat, Phil can check why the email address that you registered at the workshop. Phil can check why you don't have an account yet. You should have, all of you should have account unless you did not register, you did not reply to the OSC email. So Riyadh and let's see, who else? Rabia Sultana. Maybe you can contact Phil directly, Phil Thomas directly here, chat and give him the email addresses, and he can check why you do not have an account. Okay, the question is, do I have to install any particular software for Mac? The Mac has a terminal, the functionality called terminal. And that once you have the terminal, the SSH is already installed. So you can open the terminal and just try SSH and enter. It will give you answers like you haven't, So yeah, Mac, you do not have to. And and then for the Windows person, people who are using Windows, PuTTY and SCP, they're great. But if you want to, be a serious computational biologist, you should be familiar with Linux. And one way of installing Linux in Windows is using virtual machines. And we'll send some link. So that's another way. Install a virtual machine within your window box so that you can run Linux. Okay, Wilbur is back. It's to you, Wilbur.
Okay, thank you. Yeah, so that was a workaround for if you're trying. I'm not yet shared. Let me share the screen again. Yeah, if you're trying to run an application that has a graphical interface that we have not installed at OSC, so you can do that. And then once you're done, you just click delete. From other applications like RStudio, let's say RStudio Server, you can just come to interactive applications, right? So remember here, you don't need to install anything. Just go to ondemand.osc.edu, select your applications that have a GUI, ANSYS, Abacus, Console, MATLAB, everything that we have installed. If we don't have them installed here and best, that's when you'll have to maybe start a desktop session and then run your application that you've installed. But for things like RStudio Server, it's the same thing of just select the application, select the cluster that you want to run on, and then the version, the project number is very important, how long you expect that to run, and then the number of cores, and then you launch. And then that's going to be queued. And the reason it's queued is because you're requesting access to a compute node. So we requested one node and one core. The session is starting, right? So we're being asked to be a little patient. And then once your session has been created, you just connect to RStudio Server. And then you'll have access to RStudio Server on the compute node, just the way you'd have access to RStudio on your local machine. So you can do that. And then you can run your R applications, R commands. You do have your R console. You also do have your access to the terminal, and you can run your Linux specific commands here through R session. Just remember, the main challenge with the RStudio Server is that if you're running parallel R, in the sense that you want to request more than one compute node, to my knowledge, RStudio Server does not support that, because we only have to request one node and a certain number of cores per node. So if you're running an parallel R application, you might need to submit that through the terminal, right? Just an R session in the terminal rather than RStudio Server. So once your analysis is done, you can just come and delete the session, confirm. So that's how you would start interactive applications through on-demand. Another thing that you can do through on-demand is use this file explorer. Okay. File Explorer, you have access to different directories. All of you will have access to your home directory. And then you can, in your home directory, you can upload your data or download data. If your data sets are small in the sense that they're about just 5 GBs or less, you can easily click upload button and then you can browse folders and files on your local machine, or just drag and drop them here. You can also easily download your folders and your files. Okay. If you still taking time to learn some common Linux commands and you still want to do everything just by typing on a text editor, you can come to your files that you want to edit and you can edit, click edit. Then you'll have this window where you can actually just edit your small files, your lines of code. If you don't want to open your text editor on terminal, you can also do that. And then you'll save that. So this is the file explorer. You can actually also start your terminal in a specific folder. So since here we're already in home, or we can go to project storage. If you have project storage, you'll have something like this. You'll have /fs ESS and then the project code. And then you can go to project storage, and then you can also start your terminal window in your project storage. Let's say you want to start pizza, you can go to pizza, and then your path will automatically be in the project storage and not in home storage. So right now we are in the project storage because it's showing FS, ESS, PZS 1010. If we were in home directory, it will be showing like something like this. The users, and then the project number, and then my OSC username. That will show you that you are in your home storage. Okay. So we can go back to project storage. Let me demonstrate how to, okay, before I demonstrate how to submit a batch script, let me see if there's anything else we can do on this on-demand dashboard. So these are the file explorer. I said you can download, you can upload. We have the active jobs. I will come back to these active jobs. This will help you monitor how your job is running. For example, if you're using all the resources that you requested correctly, right? So we'll come back to this once I submit that example of a batch script. The clusters, this is just shell access. You can also look at the system status. Sometimes one of the cluster might be too busy. That means that your job might wait on the queue for a while. Let's say you want to submit a GPU job. Then you can come back, you can come to the system status. You'll notice that Owens, the GPUs, we have 83% utilization, but on Pizza, we have only 35% utilization. So you have significantly more number of available GPUs on Pizza. And if you submit your job on Pizza, it means that your GPU job on Pizza will start earlier than on Owens. So that's what you can do. Your system status, and then interactive applications. I've already talked about that. So I will go ahead and share with you just an example batch script. In this example batch script, I'm trying to perform a genome alignment. A transcriptome, I have transcriptome data. I want to align the transcriptome data to a reference genome. But the first thing I need to do is, first of all, download the reference genome and build an index, that particular reference genome. After building the index of the reference genome, then I will align my reads, my RNA-seq reads to the reference genome. So to do that, I already created a folder in my project storage called star, because I'm going to use that aligner called star. So I'll go to star, and then I created this text editor. I mean, this text file, which is my batch script file. I can open it with my, if you've been using Linux, you can open it with your text editor of choice, Vim or Nano, or whichever text editor you're comfortable with, and you can go ahead and edit it over here, right? If you are just starting out in Linux and you're not really comfortable and you have a script already that your instructor has given it to you and you want to edit, you can come to the file explorer, navigate to your folder of interest where you have that script, and then you can edit also that script through your file explorer, just like this. Okay. So in this case, we can edit the script on terminal using Nano. And then, yeah, the same things happen here. The job setup information, we are specifying resources. Here I'm specifying 5 hours. I want only one node. I'm specifying here 40 cores per node. So that means I want this job to run on pizza. And then I'm just giving it a job name. This is a genome index. I'm building an index of the genome. And then the account, I have to specify my project account, PZS1010. So you have to put the PG, whatever, the PG account. And then here, I'm just putting the standard error and standard output in 2 separate files, right? And then, so this is the job setup information. The most important things here is that you have to put the time, the number of nodes, the number of tasks per node, right? And then the account, that the project account for your analysis. And then I'm changing directory to project storage to this file, to this folder called star. And then the next thing I'm doing here is that I'm loading my software of interest. Okay, so I'm loading this GNU, and then I'm loading star. This is already installed on pizza. So I'm loading that one. And then I've already commented out this part of the code, but what I did initially was to download the reference genome. Here I'm just using simply wget, right? And then I specify the URL to the NCBI ensemble location of the human FASTA file. And then the next thing I did here was just to unzip it. And then the next thing I did here was to download the annotation file. And then I unzipped it. And then I created a folder inside star folder where I'm going to put my genome index, right? And then, so I don't need to run that. And then I'm going to run this specific commands for star. And then this is where I'm specifying the number of threads, and I'm specifying 40 threads. This is just to give you an example of a multi-threading application that you can take advantage of the number of threads. So I'm specifying here 40 threads, 40 CPUs. And when we look at my resource, I requested for 40 CPUs. That means that if you're running an application that does not have multi-threading option, let's say it only runs on one CPU, and if you run that application that uses only one CPU max and you requested 40 CPUs, it means that you'll have all the other 39 CPUs sitting idle throughout your analysis. The unfortunate thing is that, you know, those CPUs will not be accessed by any other user at that particular point in time, because you'll be actively reserving those CPUs, but you're not using them. So that will be an inefficient use of the resource. Okay? And the project code is actually going to be charged because you've requested 40 CPUs for 5 hours. So when we look at the accounting in terms of CPU hours that you've been using for that analysis, it will be, you know, those 40 CPUs multiplied by the 5 hours, because that's what you reserved. But in the actual sense, your analysis only took advantage of one CPU. So keep in mind when you're running all those applications that you're running, look at the options that they have. If the application has a multi-threading option, which you're performing an alignment or any other analysis, if it has that option, then you can put the number of CPUs there, and that should correspond to the number of CPUs that you're requesting in the SBatch directive. Okay, so we are going to submit this into the system, the batch system. I think everything is fine here. We don't need to download this again. It's already downloaded. I don't need to download that. This one is already downloaded. So the only thing I need to do is to run this. So that means I have to make sure that I'm on pizza system. So I can close this. I'm logged on to pizza, but I'm on login number 3, login node. So On this login node, I'll not be able to run analysis. That's why I'm submitting this batch script, slam batch script. And we say for submission, we just put sbatch, then we specify the script, the text file, then we get these informations, submit a batch job with the job ID. We can also take a look at the queue. So SQ minus username, and then I put my OSC username. It will tell me the status of my job, whether it's running or it's on the queue or it was killed because maybe there was an error. For example, if I was logged on to Owens and I'm submitting this job, it might be killed because we don't have 40 CPU nodes on Owens. These ones are on Pizza. Or sometimes if I'm running this analysis and I put this particular software version, and if this software version is only on Pizza, but I logged on to Owens, then I'll get an error that the software is not available. So keep track of the software that you're loading and where that software is installed. If it's installed on it's installed on Owens, then it means that you have to run your job on Owens. If your software is installed on Pizza, then it means you have to run your job on Pizza. My understanding is that most of the software applications that you're going to be using in this workshop will be installed on Owens. So for most of you, the end tasks per node here will be 28, right? For most of the analysis you're going to be performing. So our job is still running. So one of the first things that I do is to check the standard error and the standard output. So we specified this as the standard output. We can take a look at that. It's just showing us that the command is running. It has started. It's now sorting the suffix array chunks, and this will take time, a couple of hours. So we can just let it run. We can also take a look at the error file. If there is anything, we don't have any errors. It's just telling us that we've switched the compilers, right? Instead of Intel, we're using GNU compilers. And then now we can go back to the on-demand dashboard, and also there's a question, is there a way to look at all the softwares in their versions? Yes. So in the presentation, I said, if you just want to look at all the software that we have on, in this case, Pizza, you just put module avail. And I think I have those commands in the presentation that I'll share with you. So these are all the installed software that we have on Pizza, right? We also have a link on osc.edu website where you can look at all the installed software versions. And then if you're not, so you have all this software. And then if you want to load your software of interest, that's when you'll put module load. You can also check which software environment you already have in your session. That would be module list. So these are the software that you've loaded, currently loaded. And that means that even if your software of interest is available, let's say we have bowtie, right? You cannot just type bowtie and run your analysis because bowtie is not loaded in your current module list, right? So if you type bowtie and tab, oh, bowtie is already loaded. Okay. Yeah, so sometimes if the software is here, you have to actually load that particular software in your current environment. Let's say Blast, then you have to do module load Blast with that particular version, and then that will load Blast. And so since our analysis is still running, we can now go back to this on-demand dashboard and look at the active jobs, just to make sure that we're using resources efficiently. So you'll click on active jobs, make sure that the selection here is your jobs and not all jobs. We can leave this to Owens cluster. Takes a while to load. Give it a minute or two. Oh yeah, it's not loaded. Okay. Let's make sure the job is still running. Yep, it's still running. Then let's go back here. Okay, yeah. So when you go to active jobs, we have this one job that is running, and we can get more information about that job It's running on pizza, the job ID, the job name, the user, the account, the partition, it's running. We requested for 1 node, 40 CPUs, wall time of 5 hours. It's only been running for 4 minutes. And then we can now look at the usage. Excuse me. So this is running on this particular compute node, right? So we requested 40 CPUs on this node. This shows you as time goes, excuse me, shows you as time goes by, how is your CPU usage, right? So we're using almost all the CPUs that we requested, which is good. And then you can click on this detailed metrics. This will open this page. We call it a Grafana page. This is just tells you the usage of this particular node, for the last couple of minutes. And I typically like to look at the CPU load. Looks like we have 40 CPUs on this particular node. That's the maximum number of CPUs. And we've been using close to 30 of those. And as time goes by, excuse me, there will be moments whereby we'll be using close to 40 CPUs that we requested on this particular node. Okay, so this shows that really the node that we requested and the CPU that we requested are being actively used as the job runs. So that's one of the ways that I usually keep track of my jobs as time goes by. I think I will stop there and take additional questions. And if I don't want this job to continue, I can easily cancel it. I can just put as cancel and then the job ID. And then when I look at it, it's canceled. It's no longer there on the list, on the queue. Any question?
There is a question right now for you, but before that, there was a question beforehand, and I want to answer that. The question was about if you want to download VirtualBox, which version? And the answer is choose a stable version, that means slightly older, so that you do not have the bugs. And Professor Shubro, he is one of our instructors. He will put specific versions that he uses in his lab tomorrow at the Slack channel. So that's the answer. So now this one is for you, Wilbur. There's a big question for you.
Yeah, so there's any restrictions to use the available resources such as Schrodinger packages and others, like any limited number of simulations. So the thing to remember is you have a project account, and that project account has a dollar amount associated with it, which I think for a workshop or a classroom is about $500, and that can still be renewed. So if you're submitting a lot of simulations, that will eat into the allocated dollar amount for that particular project code, right? So if it gets depleted within 2 days, then nobody else on that particular project code will be able to perform analysis. And I think that's why they said at the beginning, maybe start low, see how much, and you can coordinate with Phil and to see, how much resource have been used after a couple of days. If you had your own research project, then you could, go ahead and run as many simulations as you can. We do have, but this is only for higher academics. Higher academics have $1,000 worth of credit so that they can use. And once they exhaust $1,000 of credit, different institutions will handle the bill differently. Some institutions will pay the extra, the above $1,000 usage. So yeah, I think my point is you can run as many simulations as you can. Just know that you're eating up into the dollar allocation, the amount allocated for this particular project. But if you had your own research project that is different from a classroom project, then you can run lots of more simulations. And if you deplete the $1,000 credit for an Ohio academic, then the institution can pay the rest of the amounts, or you can pay the rest of the amounts from your grants. Okay, so the number of jobs you can run in days, I can give you. So each project has a limit of the number of CPU hours they can run. For example, one job can request a maximum of 1 week wall time, right? And there's a limit as to how much wall time or how many jobs a project can run and even a user can run. And I will find that page and send it to you. Yeah. So we have limitations on, how much CPU time you will have, but that is typically after several weeks, and then you can hit that limit. And I will send you that link in a moment. And then how may I know which system Owens and Pizza will have to use for which purpose? So it depends on your pipeline. Sometimes the software that you want to use is not on Owens, but is on Pizza. So that will dictate you to use Pizza. Sometimes you're performing an analysis and you feel like Owens only have 28 CPUs per node, and those ones are not that much. So I probably will need to move my analysis to Pizza instead of using Owens. And then you can make a switch from Owens to Pizza. Remember, if you're running applications that you're installing by yourselves, you can run on either of the system, Owens or Pizza. But if you really have an application already installed on one of the systems and you don't want to go into the hassle of installing, then maybe that might restrict you to that particular system or that particular cluster. And then, yeah, I'll send you more information on the documentation. I'll take other questions.
Yeah, I want to actually comment on the Hassanur's questions. Please do not use any demanding calculations until we start the workshop. Okay. And also, after we start the workshop, the first thing we should do in the very beginning to understand the resources we have and how best to use it within our community. Okay. So again, remember, this is an in-kind, donation from a lot of people to make this happening. And ultimately, there is some dollar amount that goes there. So we have to be considerate to all of us that using that account. So we'll go into more details, but until the workshop starts, please do not start any demanding calculations. And if you want to start some demanding projects, you will have the opportunity to talk to us, the instructors, and we can find a way how best to do that. Thanks.
I just like to add that this is supposed to be, if I understand right, a multi-year project. So you got 500 credits to last until July. And Wilbur, of course, smack me right if I'm wrong. After July, you'll get another 500 credits to last you. So you do got more credits coming down the pipeline for free. I'm just requesting people be nice, keep your core count down to something reasonable, and don't, unless you have something that we want to work out, that you want to light it up a bit, let's talk about it a bit before we do so to make sure that we don't overwhelm OSC. Or Wilbur comes back to me and says, you owe me $100,000, and I have to smile at him and buy him a turkey dinner or a steak dinner to cover $100,000 worth of stuff. So please be kind and ask, right? If you're going to do something large, and then I can make sure that we can fit it in. We want you to be able to use it and learn it, but Wilbur and OSC's, niceness isn't to do your own private, huge research projects where you're, doing hundreds of hours of major computer crunching. So we'll do our best.
Yeah.
There is another question for you, Wilbur, about job scheduler.
Yeah, so we use Slam. We really encourage you to use Slam. If you already have your scripts in PBS, we used to have PBS TalkMob. You can still use them. We have a compatibility layer available that is able to translate those PBS directives to Slam directives. However, some of the conversion doesn't work that great. We have some environment variables that are not converting seamlessly from PBS to Slam. So if you can have your script in Slam, that would be great.
Okay, so I do have few requests if there is no other questions. number one is like, if you can comment on some of the best practices of using community cluster where people should be aware of other users. So that is one we want to comment. Number two, are there any limitations on on-demand system where we should not use the on-demand system, just we should be using the shell? Like what are the limit, if there is any limitation? And number three, pointing us towards an user manual. So those are the three.
Okay. Yes. So I think your first point was like considerations using HPC system best practices. Yeah. So I think the first thing that should be on everyone's mind is that HPC systems, just like any other resource, they are limited resources. Yeah. So we've just talked about the project account having a dollar amount. So it's really easy to exhaust that, and that project account is a shared project account. So other users also need to use that. So just being considerate of that. What I typically do is when I log onto the system, I try to benchmark my code before I submit a job to the scheduler. Just on the login node, I can just try to make sure that my code is running correctly. Either I can request a debug node, but if it's not something heavy, let's say I want to see whether my star alignment is going to work or it's going to throw out any errors, I can just run that quickly on the login node, few commands, and then I see if there is no error, then I submit that to the batch script. I mean to the scheduler. Another thing is obviously if you have a shared storage like project storage, you can set file permissions for your individual folders if you don't want to people to access your folder, because and I think right now by default in the shared storage, when you create your folders, you will have, my understanding is that no other users will have access to that particular folder in the shared project storage. Definitely in the home storage, nobody will have access to your home storage, so you don't need to worry about that. Don't share passwords. Don't give other people your OSC username and have them log onto the system. Yeah, but the point is it's a limited resource, so just use it considerably well. And your second question was the limitations of on-demand. To be honest with you, I haven't had any limitations on on-demand. When it comes to shell access, I can still go to on-demand, either from my laptop or from my tablet or whichever machine that I have. As long as I have a browser, I log into on-demand, I go to the shell access, and if I'm just submitting batch script, then I don't need to worry about anything. I can request multiple nodes, multiple cores, submit my batch script, and then come back and look at the results. If I want to run a GUI-based application that is not yet installed on-demand, maybe that's when I might consider using the terminal SSH with X11 forwarding, but still I can start that application through the desktop application, right? So if I go to on-demand, as I showed you, go to interactive application, then I go to desktop application. I can start a desktop, and I can start an application that has a graphical interface that is not yet installed on on-demand interactive applications. So the only other thing is that, for example, you cannot use RStudio server on demand for parallel jobs. And parallel, I mean more than one node. So that will limit you to, and I think also MATLAB, that will limit you to one node, but with all the cores on that particular node. But again, if I want to use multiple nodes for R in parallel R, for instance, I can do that in the shell terminal. And again, for the shell terminal, I don't have to use the SSH. I can just go to on-demand, open shell, submit my parallel jobs. So yeah, I wouldn't really worry about SSHing from the terminal because I haven't seen any huge or any noticeable disadvantage of on-demand. I don't know what other people think if they've used on-demand before compared to SSH through the terminal. And I think for most of the applications you'll be using, those applications are the command line based, right? Any command line based application, you can get the shell access through on demand. So you don't actually need to install anything else on your machine. Yeah.
Oh, that's great. Thank you. And I think that the third question was if there is any user manual for the.
Oh, yes.
Yes. Then we can.
So I need to compile that. But the easiest way is the first one that I put in chat, getting started at OSC. If you open that getting started at OSC, that is like a summary that takes you to different resources, right? Accounts, OSC account setup. You don't need to worry about that. Project and user management, you don't need to worry about creating a project because that already exists. And then you have transfer files to and from OSC. We have a link to that. Getting started using OSC. I'm doing this information on ondemand.osc.edu. Let me see. Batch system basics. So there's a link on batch scripts. So that will be really important. Yes, on that just user guide, batch system basics, new job scripts, the information on training. So I think the most important information for everyone here will be the batch script and the batch system, because that's where you're going to really request resources. And I can put that page also in chat. Let me see. So batch processing at OSC. So this is a very important resource. Batch processing at OSC. Yeah, we'll talk about batch system concepts, job script, job submission, managing and monitoring your jobs, scheduling policies. So everything that you need to know about submitting SLAM scripts will be in that particular link. The other one will just be like system specifications. So for example, you want to decide or you want to remember, how many nodes and how many CPUs per node that pizza system have. Then you can check on this page. So this will be, let me put it in chat. Give me a minute. It's not opening my chat here. This is pizza system spec. And then we have the on system spec. So we have the ON specs, the pizza specs, the batch processing is important. And yeah, I think those are the resources that I think could be really, really relevant, for everyone. On demand is really straightforward. If you're starting R session, just go to on demand, look at interactive applications, get R. We have Jupyter, also on demand. You can set your Jupyter notebooks over there. Yeah.
Great. You have one more question, but before you answer that question, for the participants to ask for help, what email address they should email to?
That's a good point. Yeah. So you can either send an email to oschelp@osc.edu, or if that takes long to get a response, you can send me an email. Yeah, so those 2 emails will be helpful. And then there's a question, I think, here of what is the burning rate, charge rate for classroom interactive session? So the charge rate will be, classroom usage is discounted, but we usually charge usage per hour, right? So let's say it's 0.004 over $1 for usage of one core for 1 hour, right? So if you're using 40 cores per 40 cores per hour, you multiply that number by 40. Classroom usage are discounted, but for the other project usage, I can get that information. So we have service costs, and this differs from higher academics to commercial clients. So if a user or a PI, a principal investigator, is not affiliated with OSC, then they will be charged as a commercial, sorry, it's not affiliated with an Ohio academic institution, then they will be charged as a commercial client. Let me put here is the academic fee model. Yeah, so the units are in core hours. For example, for standard compute for an Ohio academic, that will be 0.003 over $1 per core hour. So pretty subsidized. And then we have a different rate for commercial clients, but of course for classrooms and workshops, those ones are discounted. For interactive session, I don't know what you meant by interactive session. I don't know that you meant starting like instead of submitting a batch script, you start an interactive session on the terminal, but then you run it on a compute node. So the rate is the same if you submit a batch script using S-batch, or if you just start an S interactive session, the rate is the same. If you when you log on to the login node, right, before you submit any batch script, you're not being charged, or the project account is not being charged. So you can log on to the login node, and then write your scripts, look at your data, move around your data, copy your data, download your data, on the login node. On the login node, you can access your home directory or your Scratch or the project storage. So when you're doing all those kinds of things, you're not being charged, right? The project account is only being charged once you submit a batch script, or once you start an interactive session that runs on a compute node, or once you start an interactive application. Let's say you're running Jupyter or RStudio server, where you have to put in the wall time and the project code. That's when the project account is charged. But you're just logging on to the login node, and you uploading files, downloading files, creating your scripts, looking at your script, then being charged for that particular usage.
Thanks. Actually, that brings out an interesting point. I was looking at your rates. So the normal CPU rates is, let's say, 3 cents or even less than 3 cents. Hold on, what is it? About 1/3 of a cent per hour, and a GPU is 30 times more than that. So if your GPU program is not doing 30 times faster than your CPU, maybe you shouldn't use GPU. You should just stay with you should stay with the CPUs.
Yeah, that's true.
Okay.
Yeah, because you'll pay more for the GPUs. And for the GPUs, remember, you'll have to request at least one you'll have to request at least one CPU, right? Yeah. So you'll be charged for that GPU and also for the number of CPUs that you're requesting. Yeah.
Okay.
Also like to remind people not to run jobs on the Access login node. because I'll get a nasty email saying, why are you doing this? So don't run large loads on the login nodes. Keep that for the actual main course.
Yep, that's a good point, because we only have, like, if you log on to Pizza, I think we only have like 4 login nodes, and we have hundreds of thousands of people logging onto there. So don't perform analysis on the login node. If you're not sure how your code is going to run, you can request a debug node for that. You have access to that for 1 hour. So you can use that for debugging purposes.
Thank you. We are approaching our 2 hours limit. That was a very lively session. Thank you, Wilbur. And
you're welcome. I hope this was helpful, and especially for those ones who are new to HPC. Yeah, I would like to tell them, don't be afraid of big words like supercomputer. There's nothing super about supercomputers. It's just we put together all these computers together, and we've tried to simplify use of these computers, take advantage of on-demand. Yeah, and it's an interesting thing to use. So thank you for having me.